session. So I think Dr. Jason K. Ishragian would like to continue the talk more on SNN, specifically to deep learning with SNN. So let's hear to him. So before that, over to his profile. He received the Bachelor's of Engineering degree in Electrical and Electronic and the Bachelor of Law degree from the University of Western Australia in 2017 and the PhD degree from University of Western Australia. He is jointly appointed as a postdoctoral researcher with the Department of Electrical Engineering and Computer Science, University of Michigan, USA, and a Forest Research Fellow with the Schools of Medicine and Computer Science, the University of Western Australia. His current research interests include neuromorphic computing and spiking neural networks. He is a member of the IEEE Neural Systems and Applications Committee. He was awarded the 2019 IEEE Very Large Scale Integration System Best Paper Award, the Best Paper Award at the 2019 IEEE Artificial Intelligence Circuits and System Conference, and the Best Live Demonstration Award at the 2020 IEEE International Conference on Electronic Circuits and System. He was a recipient of the 2021 Fulbright Postdoctoral Fellowship, the 2021 Forest Research Fellowship, and 2019 Endeavor Research Fellowship. So over to you, Dr. Jason. Thank you.
Great. Thanks a lot for the introduction. Thanks, Alex, for organizing this pretty awesome conference. Now, the last time I gave a talk, got all these fun, exciting videos and animations. So the internet bandwidth in Australia doesn't do very well with keeping up with all of with my PowerPoints with Zoom and then showing my face to everyone. So I'll play it safe. I'm going to stop my video. I'll keep my slides going just to make sure that latency isn't a problem here. But yeah, so I think from the panel discussion, you probably have a pretty good intuition behind the type of work that I'm doing. It's at the intersection of backpropagation and the brain. Yes, how we can perhaps push the backprop algorithm, this optimization for neural nets, into something that's kind of compatible with the brain, right? So I think we're all quite aware that neural networks that are trained with deep learning, they're the state of the art in artificial intelligence, and a lot of high dimensional data, computer vision, natural language processing. Neural networks just churn through all of that really, really nicely. There's obviously a really nasty cost that comes with that. For example, OpenAI GPT-3, their language model cost $12 million to train, right? In the amount of power bills, the months of churning on a chip, it took $12 million to train a single neural net model. Meanwhile, it's a really nice analogy from Simon Thorpe at Brain Chip, where training the brain is far, far cheaper, right? Now, if we give a few ballpark figures, right? Perhaps we have 8,600 neurons, and each of those have anywhere from 1,000 to 10,000 fan-out synapses. We'll average it out at 7,000. That's a happy middle ground. Now, let's say we wanted to process all of these synapses, so all of these neurons with all of these synapses on the world's most powerful supercomputer, right? The Fugaku. And we wanted to simulate the brain on a supercomputer with a 1 millisecond precision. So that's 1,000 times every second that we need to process it. We suddenly need a system that can tolerate 600 petaflops. So 600 times 10 to the 15 floating point operations per second, right? Now, the Fugaku supercomputer can only run at 442 petaflops as far as I'm aware, and that takes 30 megawatts, right? The brain, on the other hand, only needs 12 watts. So if my brain was to try and dissipate 30 megawatts of heat of power, my head would probably just explode. It wouldn't be able to handle it in any sense, right? So the way I see it is that we can kind of go in one of two directions here. We could either A, do what Mustafa is working on. We can extract the brain's algorithm, such as spike timing dependent plasticity or Hebbian learning and random perturbation, and try and do these things in order to perform meaningful tasks. Or on the other hand, and this is the direction that I've taken, we can use an algorithm that we know works, such as backpropagation, something that's achieved state-of-the-art performance across a really broad range of tasks, and see if that can somehow fit in the brain, right? Now, an alternative perspective why the brain is so efficient is that the neural circuit is the neural algorithm, right? So think about that for a second. The brain, the circuitry within the brain is equivalent to the algorithm. Now, we're not quite there yet in hardware. We're still trying to figure this out. We're trying to figure out what's the neural circuit. But if we can figure one out, then that helps us figure out the other one, right? So one direction that I spent a lot of my PhD and perhaps the start of my postdoc in was going through these in-memory computing paradigms. And I guess I've included this in here because I think the theme of this conference is very heavily focused on acceleration, on in-memory computing, and all of these nice things that we see that can accelerate deep learning. So I've worked a fair bit with memristors here. The way this kind of works is you've got this metal suboxide with oxygen vacancies, and those pink dots there. You apply a voltage, the vacancies provide a pathway for conduction, and apply an electric field, then you can modulate this conductive pathway. And if you remove that voltage, then the ions hold their position. So that's a sense of non-volatile memory. So we're programming the resistance of this device. We're measuring the resistance by applying some sub-threshold voltage, and we read out the current. So research on analog storage is kind of ongoing. By modulating the length and the width of conductive pathways, we could perhaps obtain more storage states within a nanoscale memory. It seems as though 8-bit memories are kind of the norm with tantalum oxide memristors. But yeah, we're seeing retentions of 10 plus years, and in some devices, endurance is 50 million cycles. But as I mentioned, a very conservative estimate that we see from industry is 10,000 cycles. So of course, there are some trade-offs with this, but having said that, it's quite simple to fabricate because it's just a metal insulator, metal structure, right? So we've got memory. How might we process, right? And where I'm going with this is fairly obvious, I think. I mean, in conventional von Neumann architectures, we've got a system where our processor is separate from our memory, right? So it takes a lot of time to shuttle information back and forth, and that's considered to be a bottleneck. So what we want, ideally, is to be able to co-locate memory and processing. And so that's one potential direction that memristors have opened up a lot of opportunities in. And currently, with a lot of the state-of-the-art deep learning accelerators, they kind of go in a very similar direction. Rather, they just use SRAM, or in some niche cases, DRAM, and they distribute this memory across a chip, perhaps within systolic arrays or right next to your processors. So you've got near-memory computing or in-memory computing that is aiming to reduce the time it takes for information to be shuffled back and forth, right? So how can we actually process this stuff? So this is a tantalum oxide array that was fabricated in the clean room here at University of Michigan. Actually, I'm not currently in Michigan. I'm in Australia. I'm about 2 hours south of Mustafa. I somehow haven't been able to see him in 18 months, but once I guess borders are open again, then maybe I'll go visit him. So we fabricated this about 2 years ago in Michigan, and the idea is if we structure our RAM, which I've represented here as just simple resistors, into a crossbar array, then we can actually parallelize a lot of computations here. So we might apply a voltage at the input. It could represent a pixel value in an image, and that memristor or that device is going to draw a current. We do this in parallel, and by Ohm's law, Kirchhoff's current law tells us, the Ohm's law will tell us that the current drawn is simply a multiplication between conductance and voltage. And concurrently, we've got Kirchhoff's current law that says, hey, well, along a single bit line, all of these currents add. And I think this is a fairly common concept of bitline summation. So I won't go into that in much detail, but the effective takeaway is that what you're doing is vector matrix multiplication, right? Your vector is voltage, your matrix is conductance, and we can program all of these values during the training process or during a write process. And inevitably, we get a series of output currents that we pass through an ADC, and hey, there we go. We've done matrix vector multiplication. And that's really nice because that's actually the dominant operation in multi-layer perceptrons or in deep learning. So it's once you pass that through an activation unit, then it's effectively a one-to-one correspondence. So the goal is to store all of our weights on chip or co-located with our processor in a similar way to how neurons and synapses are physically meshed together in a sense. And in doing that, we can perhaps achieve in-memory computing in a way that's akin to how neurons in the brain not only store our memories, but also encode and process all of that data. And I want to stress that we're not trying to replace CMOS at all. We're trying to work side by side, or I guess vertically in a more literal sense. So RRAM or resistive RAM is typically fabricated in the back end of the line between your final metal layers, and we control which cell we access simply by asserting our word lines, just like in any other memory array. So this isn't all that exotic in my opinion. So we spent a bit of time assessing, so this here is a chip that was fabricated by my group before I joined them in 2000. The chip was developed in 2019 and then published a year later. So it was led by Fushi Kai and Professor Wei Lu, who's my supervisor. So it was taped out at 65 nanometers. It was a mixed signal chip. I think Mostafa's gone through a little bit about mixed signal processing. And the main metric that everyone is looking for is the number of TOPS per watt, tera operations per second per watt. So how many operations? And an operation here is defined to be a single 8-bit multiply and accumulate. How many of those multiply and accumulates or matrix vector multiplications can we implement per second with 1 watt power? Right. So clearly they're beating Google's edge-based TPU system at its time. And I guess keep in mind that this is a 65 nanometer node. So as advanced technologies mature, then in theory, we would have calculated it to come out to something like 37.9 TOPS per watt, but that's a little bit of conjecture. And I guess this can answer one of the previous questions that came up. How effective is quantization in training? And I guess here, see a floating point accuracy on the ImageNet dataset versus several other methods versus MobileNet's architecture. And it's generally quite robust. You're losing, I guess, 2%, 2 to 3% at most. Now, MobileNet does take a bit more of a hit in accuracy, but again, MobileNet is a very resource-constrained, small deep learning architecture. And so we're kind of not surprised by this result, whereas VGG16 is over-parameterized. It's very large. It has millions and millions of parameters inside of it. So let's take a look at a few thoughts about this. So there's going to be a few challenges in trying to scale this kind of work up. Now, we saw that we went from, I guess, 2 TOPS per watt in Google Edge and Mythic's flash-based accelerator to something that's close to 6. Now, 1.5 or 2x improvements are generally not sufficient to justify startup costs for a new process, right? You're investing billions and billions of dollars just to build up a new fab, but the 2x improvement, it's just not enough. We need something more, right? And another challenge that we're facing here is scaling. Right? Advanced processors are really not optimized for analog operation. I mean, everyone's building microprocessors. Intel's main moneymaker are their processors. So everything is done with digital in mind. Right? Now, the main killer, in my opinion, the analog to digital converters, because we have to convert that analog current into some digital output, right? And ADCs account for 91% of the area occupation on this chip and 80% of the total power consumption, right? That's huge. Normally we're faced with memory access as being the problem. But here we've kind of traded off one problem for another problem, right? So that's quite an issue. Next, we've got large programming currents. During readout, it's fine because we can use sub-threshold voltages, but when we're writing to the memristors, we're injecting fairly high currents, right? Now that means that we have to have larger pitch. We have to have larger transistors to tolerate that higher voltage, right? And so my point is that these state-of-the-art results that at the time, they were great, but we really need more, I think. So what we were looking at, what the questions we were asking were, okay, how can we make this better? What do we do? Do we tackle it from a hardware perspective? Do we try and optimize our ADCs a bit more? And that's what we started to do. I was trying to design some SAR ADCs, and then I guess COVID hit, and I moved back to Australia to work remotely, and semiconductor shortage hit as well, and everything just went to chaos. And so we said, hey, how about we go and think of some algorithm level optimization? Now, what I think is beautiful about spikes, well, it's just one of many things, are that spikes are, I guess in a sense, they're digital, right? I mean, a spike is either a 1 or a 0. It either happens or it doesn't happen. So that, if you can convert this high precision or analog noise intolerant array with a single spike, then that effectively addresses your ADC problem, right? And so this kind of leads me to what I've been working on for about the past 24 months now. How can we take spiking neural nets and do something useful with them? So I ask, what's so good about the brain anyway? I think a lot of other speakers have addressed this in quite a nice way. And during our panel discussion, I also went through the 3 S's. The first of those S's is the spikes. Now, spikes are great. And I hope to convince you that spikes are great by the end of this. Now, if you think about a neuron, right? All these things in our brain consisting of neurons is the atom of the brain. Now, if I'm an experimentalist and I take an electrode and I stick it into the neuron body, right? I'll see a lot of fluctuations around this area. I'll see a lot of noise. I'll see a lot of voltage jumps and decays. I'm going to see a lot of variation. But the moment I take this electrode and I move away from the body, let's say I move 1 millimeter away from the soma, from the neuron body, then all of a sudden, all of that noise disappears, and all of that noise is attenuated. All of that variation is gone. All I see is a dead signal until an action potential or this spike occurs, right? So what that tells us is that most neurons are communicating via discrete bursts or discrete packets of information known as action potentials or spikes, right? Now, in general, most neurons don't actually care about the shape, the amplitude, the width of these action potentials. All they care about is whether or not they occurred. So in a lot of neural coding studies, we approximate this action potential into, well, this what looks kind of like a Dirac delta, just this sudden occurrence of a spike. And rather than infinity, we set it to 1. So we've got a series of zeros when there's no action potential, and then suddenly it fires, your neuron fires, it triggers this 1 down the axon, and great things happen. A lot of other neurons feel that. Now, that's all. There's also a lot of other advantages to this, right? Because, well, if we take 1s and 0s on a microprocessor, those are far easier to operate on when you compare them to high precision or fixed precision or fixed integer values, right? If I take this 0 and treat that as my input, I multiply it by a weight, then that's just 0, right? So eliminate the readout while my neuron is quiet. Now, on the other hand, if I take 1 and I multiply that by my weight, well, that's just a weight. So I'm trading what's potentially a complex multiplication process that's filled with carry propagation delays with a single memory readout, right? So that's really nice. And another thing that's really nice is that layer-to-layer communication. What's classically very expensive and can take a lot of energy and a lot of latency to transmit information between cores or between layers. Now we're swapping that high precision floating point value, and we're only communicating 1s and 0s between parts of our chip. So that's spikes, that's our first S. And the second S is sparsity, right? So neurons spend most of their time at rest. They're usually quiet. And that means that most of your activations are 0 at any given time. So you have very sparse data structures. So if you look at this kind of complex looking vector, it's filled with zeros. It's really inefficient for me to describe it by saying 0, 0, 0, etc., 7. It's far more efficient for me to simply say 7 at position 10, 5 at position 20. Now that's far more efficient. And this data structure is actually also very efficient because memory only will increase as the number of non-zero elements increases, right? If my neuron is quiet and it keeps staying 0, then my memory or the storage that it takes to hang on to this sparse variable, this sparse vector or matrix or tensor, it's not going to increase in memory, theoretically. Now, the final S, and again, this came up in our panel discussion, but it's static suppression or event-driven processing. So the sensory periphery only processes information when there is new information to process. I won't go into too much detail because I think we got the feeling for what this is. But effectively, if your background is static, then that's effectively a whole heap of zeros. But you see this moving car, and all of a sudden you get these triggers, and you get ones. So what does that look like? So we were talking about dynamic vision sensors. And so this is a camera that came out of Kobe Delbrook's group, I think back in 2014. But the idea here is that because each pixel is asynchronous to one another, these pixels are only detecting luminance changes, right? So if your luminance increases over time from some dark value to some brighter value, only then is an event, or only then is a pixel activated, right? And because of that, because most of your pixels are actually quiet, what that means is that you've got this camera that is very low power. And because it's very low power, you can crank up the clock speed and get this really cool slow motion microsecond resolution. So that's quite an interesting way to use this spiking paradigm from the sensing level, right? So this is just sensing, and then we put this into a spiking neural network to process it. So I guess how are people using spikes to train neural networks? I suppose that's what we really want to know. Now, one of the state-of-the-art, most common methods that we're seeing out there is simply training a non-spiking neural network and converting that to a spiking neural network through optimization techniques. And it's, I guess, state-of-the-art in most complex tasks that use spiking neural nets, so that's quite nice. And training deep networks is actually really, really simple. If you can train a deep learning model, then you can convert that simply into an SNN. So this shadow training approach is quite nice. Now, a few drawbacks to this. Well, firstly, this spiking neural network is always going to be an approximation of your artificial neural network. So this guy will very rarely, quite frankly, I've never seen it happen, but this guy is never going to beat this guy, not in terms of classification accuracy or performance. In terms of power during the feed-forward process, absolutely. This is where the spiking neural network shines. But during training and in terms of classification accuracy, we're not there yet. Secondly, another drawback of this is that temporal ANN, or non-spiking neural network conversion, is thoroughly underexplored. Right? So all of the techniques that I'm seeing out there are typically tested on static data sets like ImageNet or CFAR10. And spiking neural networks, or brains, are these online learning machines. They're constantly changing, and spiking neural nets are also constantly changing. So we're kind of not exploiting their capability or their capacity to model temporal information in that sense. So there's still a way to go there. And secondly, of course, they're biologically implausible, but I'm not too concerned about that. I'm more concerned with whether or not it's useful. But to go back to some of the pros of this, I saw Shichi Liu's group from ETH. They published at ISCAS just this year. They trained a 20-layer autoencoder for segmentation in video. And so that's really nice. And there's a lot of really good conversion packages online that make this whole process very simple. One of those, the most popular conversion tools, was by Bodo. It was published in 2017. It's called the Snn Toolbox. And this is quite crazy because despite being released in 2017, it's still highly relevant today. And I kind of think that 4 human years are equivalent to 400 deep learning years. It's such a fast-paced field. So it's a testament to what a nice tool it is. What I'm really interested in isn't making approximations. It's rather in natively training a spiking neural network of its own accord, right? So some of the pros here is that, well, it's no longer bound by the upper limit of ANN performance. And secondly, well, I guess this is a little bit more loose, but biological plausibility depends on the learning. So biologically plausible algorithms such as STDP and many of those unsupervised approaches, they are insanely efficient, right? And I think Mostafa really drove that home. They're really, really efficient in terms of reducing your power bills, but they really struggle with complex tasks. So although backprop and gradient descent made up of many constituent steps. So many people argue that backprop is not biologically plausible. And in its rudimentary or basic form, I would have to agree with them. But there are ways to kind of mesh backpropagation into methods that might actually fit into the brain. So one example that I mentioned during the panel discussion was, I guess, random feedback alignment. It takes elements of backpropagation, it takes elements of a global error signal, but it uses local noise. It uses noise and it uses local gradients in order to perform updates. Another approach is, rather than performing backpropagation directly, if we loop around the error signal back to the input, then there's a method known as forward mode auto-differentiation that we can use in order to train our spiking neural nets. So we're not sure how optimal this is just yet, and it's very unlikely that the brain memorizes every single feed-forward pathway. But this is a little bit of intuition as to why backprop isn't so impossible. Not once you structure it right. A few of the cons of backprop. Well, it's not very efficient on modern hardware. Right? Spiking neural networks are temporal. They are sequential neural networks. What that means is that you're storing a whole history, a whole series of time steps of gradients, and many modern hardware and a lot of modern Python packages just haven't optimized that. And part of that, an extension to that, is because there's less manpower invested in this. We still haven't figured out the best practices to training SNNs. And that actually means that they're very sensitive to hyperparameters. Change one small thing, then your network may very well go completely out of whack. So to address some of these issues, I took on a bit of graphic design classes back when I was 15 years old. I have developed a Python package called SNN Torch. It effectively takes gradient-based learning and integrates them with spiking neural nets. It's an open source project on GitHub. So if you were to simply Google SNN Torch, you don't need to memorize my tricky surname. You can just type in SNN Torch into Google and you can see what this project is all about. But we're trying to optimize SNNs using backpropagation. I've integrated very recently real-time online learning as well into this package so that you can perform variations of backpropagation on the fly while you're also reading in input data. It's seamlessly integrated with PyTorch. So if you're anywhere at all familiar with PyTorch, then you are basically an expert at SNN Torch. And of course, it's CUDA accelerated and it's lightweight enough to run on a CPU. So that's the package. Let's take a look at what the types of things that we can do with it, right? Before we go into how we might train a network and how we can make it learn, let's understand what spikes even mean. Right? We know why they're good, but how do we assign meaning to spikes? And there are several different interpretations here. I think that this is quite funny. There's this huge war that's been waging between rate codes and temporal codes. If you're not too familiar, rate codes are the idea that information is stored in the spike count or firing rate of a neuron. Right? A neuron needs to fire multiple times, and depending on how many times it's fired, that's where the information is stored. Then on the other hand, a temporal code doesn't really look at the number of spikes or the frequency or the rate of spikes. Instead, all it wants to know is when did the spike occur, right? The timing of the spike, timing of perhaps one single spike or the timing between two spikes is what matters. Right? And so STDP is kind of like a temporal code in that sense, in that you're looking at the timing between two spikes in order to update your synapse. So there's this sacrilegious war between rate coding and temporal coding communities. It's kind of like Bayesians versus frequentists, or like Australia's cricket team and India's cricket team. Very, very, very intense war going on here. But in general, I would argue that the brain very likely uses temporal codes for the dominant part. There's a really nice paper called "What is the Other 85% of B1 Doing?" by Bruno Olshausen. And he basically conjectures from power and metabolism arguments that 85% of the brain must be using a temporal code. And why is that? Well, because of power, right? Well, if if every neuron was to encode information in a spiking rate, everything that I saw, if all my senses were encoding data in a rate, in multiple spikes, then that's too much electricity being generated in my brain. That's too much power being dissipated. My brain would melt, right? So he conjectures that 85% of the brain must be operating off a temporal code. There are several other really, really convincing arguments as to why the brain operates in a temporal code, but hey, I think that's probably the most interesting one to me as an electronic engineer. Now, another thing to think about is that that's the brain. Our senses, on the other hand, our retina, our factory senses, our haptic feedback, our touch, nerve endings, typically these are actually fairly well established that the input from our surroundings, from the environment, are encoded as a rate. So you can think of it like this. Senses encode information as rates. A spike rate is transferred to our brain, and our brain somehow meshes and warps all of that rate, all of those many, many spikes from our sensory input into a temporal code. So that's at least my opinion on what happens to the brain. Now, in practice, if we were to take this onto a spiking neural network and we wanted to train it using the backprop algorithm, what I've personally found is that rates, even though they're not necessarily as power efficient, they are actually better for error and noise tolerance. Well, why is that? Well, information is now distributed across multiple spikes. So if one of those spikes fails, that's okay. We have plenty of other spikes where that came from, right? Another advantage is that rates enable faster convergence when using backprop, right? Because if you think about it, a spike is effectively allowing a gradient to flow back from your loss function. If you have this error signal in your network, then a spike allows that error signal to flow back. And if you don't have a spike, if it's a zero, then that gradient is effectively zeroed out and your network can't learn anything. So in this case, even though we're trading more power, if you have more spikes in a rate code, then you get more learning, right? Now, on the other hand, I mentioned that timing is typically better for power efficiency and for latency. So I'm not really here to tell you that one is the best and the other is the worst. I mean, I think I've given you a pretty balanced opinion on what's probably biological and what might be useful in an actual neural network. So hopefully you can take that away and maybe make use of it the way you see it. So if we want to take these concepts onto a neural network and actually do something useful with it, we need to separate this concept of spike encoding into two separate views, right? We have our inputs and then we have our outputs. So our inputs, showing you an example of the number 7 from the MNIST dataset, just static handwritten images. We've got the option of simply passing this static input, the same thing at every single time step, into our network. We have the option of rate coding it, where we take the bright pixels and give them a really high firing rate, and we take the dark pixels and give them perhaps a really slow firing rate or no firing at all. And we could pass that firing rate into the network at every subsequent time step. You could also do this as a latency code where your bright pixels fire first. So perhaps this bright pixel over here might see a 1 at t equals 0 and then 0, 0, 0, whereas your black pixels would go 0, 0, 0, 1 at the very end. So that's spike encoding at the input. Right, we can encode data or we can simply apply it as a constant current injection, and that might be fine. But then on the other hand, we also have our output. Right? We need to somehow make our network fire in a way. We need to teach these output neurons to fire in a way that we can interpret from, right? So in this case, let's say that this orange neuron is our correct class. Now, if that's our correct class, if I was to do a rate code, I would train my network such that this neuron fires the most frequently. If it was a latency code, all I would care about is making this neuron fire first. And then all of these neurons can fire later or never fire at all. So in a trained neural network, now let's see if this animation works. So I converted the static MNIST sample into a rate. So you see that the yellow pixels are kind of probabilistically firing. There's a high probability of firing if it's a brighter pixel. And then the blue is basically just dead quiet neurons. And I passed that into a network. I trained a very basic network. I'm not sure if my internet bandwidth can handle this. I think it's working. But what you're seeing is that as we move forward in time, in a fairly weakly trained network. I'll pause it here. What you see is the number 3 gets the most spikes. By time step 40, we see number 3, it's correctly classified that a rate-coded network is classified that it's the number 3. But number 5 is also a contender, right? Now, if this was a latency-coded or a temporally coded network, then there is a very good chance that this number 5 might have fired first. And then that could have effectively caused us to get the wrong classification here. But, with better training, with more epochs, with certain tips and tricks that are taken, we could perhaps suppress this number 5. But it also kind of makes sense because this 3 could also, if you're not wearing your glasses, it could also look like a 5. So that's all well and good. Let's do something. Let's go down to the basic level of a leaky integrate and fire neuron. Right? We've talked about what we're trying to make the network do, why we're trying to make it do that. Let's see how the neurons behave. So topologically, artificial neural nets are exactly the same as spiking neural nets. They're connected in the same way. We can do convolutional SNNs, we can do recurrent SNNs, residual transformers, LSTMs, all of the good stuff. It's all the same. The only difference is the neuron model, right? So how does a spiking neuron model behave anyway, right? Now, if your neuron is sufficiently excited, we excite it with these input spikes or DC current injection. If it's sufficiently excited, then it generates this output spike, right? And this can kind of make sense because when you take a look at this, rudimentary view, cross-section of the neuron body. This is just the neuron body over here, without the inputs, without the outputs. What you have on the inside is saline solutions, ions. Right? On the outside, you have more ions or sodium ions. In between, you have this thin membrane insulator, this lipid bilayer that sort of protects the inside from the outside. And so if your inside and your outside is made up of conductive ions that are insulated by something in between, that's basically a capacitor, right? You've got charge collecting up on 2 conductive plates, so you get a capacitor. Now, at the same time, this membrane here is opening and closing to allow some of these ions to diffuse from inside to outside, outside to inside. And that leakage of ions from intracellular to extracellular medium can be modeled as a current leakage. And so that current leakage can flow through a resistance. Right? So you might know where I'm going with this. You have a capacitor, you have a resistor, and you have a really simple RC circuit. And all of those input spikes are being generated by this input current source. And so let's take this top node, this top plate of the capacitor to be our membrane potential. I might interchangeably use the variables V and U to represent membrane potential. So try not to get confused by that. But this modeling of the leaky integrate and fire neuron can be dated all the way back to 1907 by Louis Lepic, who was, at the time, it was very, very difficult to design current sources, and they didn't have the resolution to probe individual neurons. So he took the nerve fiber of a frog, the frog's leg, and he applied a current source of varying amplitude, varying pulse width. And he basically used that extracellularly in order to determine the relationship between your driving current and the threshold of this neuron, or how the neuron responds, right? So it was a very, very hacked together experiment. So let's kind of see what his results look like. If I inject this input current, I'm not going to go into any ordinary differential equations or any of that. We'll just keep it purely qualitative to make it easy to follow. If I inject a step current, then this membrane potential exponentially relaxes to some steady state value. Steady state value is simply your current multiplied by your resistance. Now, let's say I cut off that current at some time here. Well, everything here stays the same, but you get a decay with an RC time constant. Now, let's deliver this like a similar amount of charge in half the time. So we double the amplitude in half the time. The rise time speeds up, but your RC decay is going to be the same. Let's do that again. Let's just make it more extreme. Your rise time gets faster. Now, in the limit, when we have the area under the curve set to infinity, if you make the pulse width approach 0, then physically this is impossible. We can't actually apply this using a regular experimental setup. But that spike, if you integrate it, then the charge delivered actually makes kind of sense. It makes sense. You effectively get this instantaneous rise time and a decay that follows here. Right? So if we take that spike input, this is what we get from our membrane potential. And maybe we'll apply a spike train because other neurons are transmitting spike trains into this RC circuit. And so that looks like this. So we see this decay, we see this leaky, right? Leaky integrate and fire, that's where leaky comes from. But we're also superimposing these on top of one another. That's our integrate. A leaky and we're integrating. There's one more element to this recipe that we're missing, and that's the fire. So before we get to the fire, I want to show you how we can convert all of this information into something compatible with neural networks, compatible with the backpropagation algorithm. And that arises if we discretize all of our steps, if we discretize this signal, right? We can take our voltage at our next time step, and we apply our input here. We apply our input spike. So effectively, this spike is being added to our membrane. That causes the jump. And then at every subsequent time step, we have a decay rate of beta. Right? We have a voltage, and that's decaying at a rate of beta. So the ratio between time step 2 and time step 1 is going to be beta. So if beta is less than 1, then you're going to get an exponential decay back towards 0. All right, so that's how we discretize this equation, and that's going to be really important to us. So let's try and get this firing action going on. Let's inject this spike, and we'll attach this thresholding mechanism. So our membrane response is going to integrate, it's going to leak, and then finally it reaches the threshold. Once it reaches the threshold, that voltage is going to be reset back to 0. It's going to be reset, and we get a spike at the output. So that output, I haven't shown it here, but the output is transmitted to the next layer of your neuron. We can condense this into our leaky integrate and fire neuron node. We replicate this millions of times and generate a spiking neural network. And it's only communicating with those single bit spikes from its input to its output. And the traversal of the membrane potential is sort of like a internal feedback that doesn't need to be communicated to anywhere else on the chip. So just to give you another visualization of this, if we have our input, then it's going to go back through this decay. And then at the next time step, the decayed voltage is going to be summed together with the input. Then it goes back and it checks, hey, am I greater than the threshold? If so, I generate a spike. And if not, I just keep decaying. Right? But that's just a recurrent representation of a spiking neuron. We can also represent this in an unrolled computational graph. Right? We have our input where we go from left to right, we're incrementing in time steps. And if we go from bottom to up, we're going from the start of the network to the top of the network, but really this is just one single neuron. And if we have an input, we're doing the exact same thing as this recurrent representation. Current goes to the voltage, it checks, am I greater than the spike? Am I greater than the threshold? If so, then I spike. If not, I go through this temporal connection beta, I decay by beta, and I decay 3 times. And then finally, if an input comes in, stimulates me to be greater than the threshold, then I spike. Right? So that's effectively what's going on. But we want a learnable parameter. Right? Neural networks have some learnable weights in there. And so this current is simply a product of an input and a weight. And these weights are shared over time. So this W is effectively equal at every time step. Right? And this X could be current stimulus. It could be a spike from a preceding layer of neurons. So this W is what we're trying to learn by using the backpropagation algorithm. So from here, we're getting to some output and we want to calculate a loss. And there's many different ways that we can do this, where we trigger a series of spikes over time to generate a loss. And I'll be very quick about this, but where I'm going is that we still haven't completely figured out the most optimal way to do this. So we're getting there. Right? But let's say that we have 3 output neurons and one of them is this green one is a correct class. Now, if we were to apply a cross entropy rate loss, then what would happen is your correct class would be encouraged to fire a maximal amount of times, and your incorrect classes are just going to be suppressed as much as they can. Then an alternative way is implementing a mean square error count loss. So in that case, you're basically trying to say, all right, I want my correct class to fire a certain number of times here. I want the correct to be 4, and perhaps I want my incorrect to be 2. So in this case with neuron 1, it's incorrect. So 2 spikes, perfect. That's exactly what I was aiming for. And for a rate code, it'll say, yep, 4 spikes is greater than 2 spikes. So that's still fine. 0 is my correct class and 4 is what I wanted. 4 is my target. So that's all well and good. Why are we getting incorrect neurons to fire? Well, like I said before, if you have spiking, then you have a gradient flowing as well. If you have a gradient flowing, then you have learning, right? So it's not always optimal to push incorrect classes to 0. And you've also got a mean square error membrane loss, so we can micromanage the internal state of the neurons. So this is a bit of a hack because now we're operating on the hidden variables of these neurons. So this may not necessarily be the most acceptable method here, but we can train the membrane potential at each time step, and that can potentially be useful for temporal codes. Right? So in this case, perhaps we take 0.9 volts and try and encourage it to 1 volt or to a threshold. So this recurrent representation of neurons, I'm going to quickly go through this because it relies on backpropagation detail, but all of these terms are perfectly calculable, but what we don't know is how can we go from spike to voltage? Right? Now, if our weights change a little bit, then what you're going to see is your voltage is actually not going to necessarily alter the output spikes. If you think about it, your voltage needs to be greater than your spike, greater than your threshold to induce a spark. And if we take the derivative of that, then it's 0 everywhere. And so that leads to what's known as the dead neuron problem. And so a common solution to this is to use the surrogate gradient approach, which smooths out the gradient. There's several other approaches that I've implemented that also work really nicely. I'll refer you to an archive paper that I put together, so I won't go into that in much detail here. But anyway, we take that surrogate gradient and we can effectively use backpropagation through time to transmit that error signal. Right? There is a link between this and STDP. I'm happy to take any questions in question time in order to address that. But we've also got online learning mechanisms that are enabled in Snn Torch, which use forward gradient propagation and real-time recurrent learning. So a lot of nice tips and a lot of nice tricks in order to make learning a little bit more efficient. Population coding, just in the interest of time, I'm kind of going to fly through all of this. Population coding lets you basically use multiple neurons per output class. And like I said, more spiking means a stronger gradient signal. So population coding is really nice for encouraging a gradient to flow during the backpropagation process. In terms of numbers, we've trained this all up on Loihi, and we've shown that using a variety of neuromorphic chips, we're suddenly able to get 100 to 1,000 times better performance in terms of your energy delay product without taking a hit in accuracy. And this is done on a real-world data set which uses EMGs combined with dynamic vision sensing processes. So there's definitely a really strong place for SNNs here. And previously with memristors, I was saying, oh, we've got 1.5 to 2 times improvement. Well, no, now here, we're able to see orders of magnitude of improvement. And so if we apply this to in-memory SNN processing, we can effectively replace these ADCs, these high precision currents, with simple readouts of single spikes, right? So this is suddenly a lot more noise tolerant because we're communicating simple digital spikes down long lengths of wire. So I think I'll leave it at that. There's plenty more that I could talk about, but I'll leave that to question time in the interest of time. Yeah, I'll let you take it away.
Yeah, thank you, Jason. So if you have questions, please type that in the chat, and probably Jason can answer that in the chat itself because we're a bit off with the time. So thank you very much. So if there are questions, please do type that into the chat. Okay, we'll move to the next talk. Let me see if